Got it? All right, I will begin with a word of prayer. So, Heavenly Father, we I can't whistle. Oh, that's all I got. Heavenly Father, we thank you for this day and for quizzes, which are fun and relaxing. And I pray that you'd help this lecture to be useful to the students, that we'd all learn something together, Lord. In your name I pray. Amen. Yeah, we should do that every day. Like, it's so relaxing for me. I mean, like, no? Okay, so what I want to talk about today are a few different sort of geometric applications to differential equations, first order differential equations. My ultimate goal being to talk about integral curves or flow lines to vector fields and the problem of finding orthogonal trajectories. Before I get there, though, I'm just going to take a step back and talk about level curves versus parameterizations of level curves, because I think it's something that, you forget about. We need to sort of revisit how this whole thing ties together. So I'm going to start with talking about level curves and parameterizations of level curves and their calculus. So what's a level curve? Something like f of x comma y equals to a constant, right? What's a parameterization of a level curve? So let me call that constant k for the second and say that this is the curve C. Suppose C is the solution set to this equation. That's a level curve, right? It's the level k curve with the level function f. A parameterization of the same curve would be something like what? We get x equals to, x of t and y equals to y of t. I mean, maybe, some calculus book might give this call this little f of t and little g of t or something, but I'm going to be lazy and just say that x of t is the formula for x and y of t is the formula for y. And if it's a parameterization, if this is a parameterization, all right, of C, then what's that mean? That means that f of x of t, y of t is equal to what? K, right. If it's a parameterization of that same curve, then that's equal to k. Now calculus, what calculus can we do with a level function? What's the main thing we do calculus-wise with a level function? We can calculate the gradient of f, right? It's partial f, partial x, partial f, partial y, right? What could you do with the parameterized curve? What's the relation between the parameterization of C and the gradient vector to C? I mean, what can you say about the calculus of the path that parameterizes the curve? How do the derivatives of this path relate to the gradient vector? How do we discover the relation? They're perpendicular, right? And how do we know that?
Doesn't that equal 0 when it comes together, right? Or something like that?
Right. I think you're on the right path, but it's very simple. All we do is we differentiate this expression, right? If you take the derivative of this, we use the chain rule. What's the chain rule say for functions of two variable? The chain rule here, what it looks like, right, is partial f, partial x, dx dt, plus partial f, partial y, dy dt, right? Of course, the partial derivatives of f with respect to x and y are evaluated at x of t comma y of t, right? So to be more pedantic, this is really the gradient vector of the level function evaluated at the path x of t comma y of t, dot product with the velocity vector dx dt, dy dt. And of course, on the other hand, this is equal to 0, right? Because this is a constant, derivative of a constant 0. So, which is exactly what you're just telling me. The tangent vector to the path is going to be perpendicular to the gradient vector, right? So if we draw a picture, if this is, if this is f of x comma y equals to k, right? Then we can picture the the gradient vector looks like this, right? This is the gradient vector field. Looks like an amoeba or something, right? See here, something from biology maybe. See here. So here I'm plotting nabla F as it's known, right? And if you pick a particular point, right, supposing that the parameterization has a counterclockwise orientation just for the sake of discussion, of course you got choices, right? Then this right here would be dr dt, my usual Calc 3 notation, dx dt, comma dy dt, right? So this is the relation between the level curve and the gradient vector field, right? Any questions? Yeah. I can't. The gradient vector is always in the plane of the level curve. Yeah, because we're looking at functions of two variables, so the gradient is a vector in the plane. Now you're thinking like three-dimensionally maybe. You're thinking about a level surface, perhaps, f of x, y, z, right? In that case, the gradient vector we learn points normal to the tangent plane to the level surface at the point. Yeah. But it always points perpendicular to the level curve, right? It points in the direction of maximum increase in level, right? If you want to level up, follow the gradient vector, right? Okay. So, if we're solving, right? So here's a question for you guys. If we solve m dx plus n dy equals to 0, right? What's the geometric relation with the vector field f equals to m comma n? And I've been vague here. Geometric relation of what? Geometric relation of the solution curve, right? Let me make a leading comment for you. If we have m dx plus n dy equals to 0, formally, what you could do is just divide by dt, right? M dx dt plus n dy dt is equal to 0, right? Now, dx dt and dy dt you could think of as the velocities of a parameterization of your solution. And so this says that m comma n dotted with dx dt dy dt is equal to 0. Let me write a paragraph what I'm trying to say here. So what I'm saying is if we parameterize the solution curve to star, right? Then we can see the solution is blank to m comma n. Parallel. That's what you guys are, that's what I'm tempted to think of naively, is that they're parallel, but that's not the case, right? This shows that the dot product of m comma n and the velocity right? The velocity of the parameterization of the solution curve, which reveals its geometric nature, right? This reveals the direction of the solution curve. It says it's perpendicular to the vector field. That's what that says. Let's try it out. If I look at f equal to, let's say, x comma y, right? This vector field's pretty easy to plot. What's it look like? It looks like this, right? It's always pointing radially outward, right? So it gets bigger and bigger the further you are from the origin. I don't really care so much about the magnitude. My point is directionally, it's always radially outward pointing, larger and larger and larger magnitude, right? Do we agree? We've all had calculus 3. We should know what vector fields are and have some sense of how to plot them, right? I'm not overstepping my bounds. I shouldn't be overstepping my bounds. So, my assertion is if we solve x dx plus y dy equals to 0, we're not going to get lines through the origin. Right? Lines from the origin would be the lines which line up with the vector field, right? So-called flow lines of the vector field, right? Flow lines are lines or curves that, when you look at them, the tangent field to the flow line matches the vector field along the flow, right? I mean, this is what flow line means. My assertion is that this will not give us flow lines. My assertion is that the solution to that is going to be circles. And in fact, that's pretty easy to see because this is exactly the differential of 1/2 x squared plus 1/2 y squared, right? So the solution is 1/2 x squared plus 1/2 y squared equals to a constant. I say that constant is 1/2 r squared because then I get to write this, right? You're like, your way of solving this is dark magic. Fine, integrate separation variables if you like. Does it make you feel better if we do this? Y dy equals to minus x dx, and then dy dx is equal to minus x over y. So y dy, well, this is dumb. Minus x dx, but now we've gone full circle. Pun intended. And then integrate both sides, and then you get 1/2 y squared equals to minus 1/2 x squared. Don't write this down. Plus a constant. It's circles. It's like my first example, probably, usually. But look at, are circles flow lines of this red vector field? No. They are exactly what I said. They are perpendicular to the vector field, right? See that? This is a solution curve. It is perpendicular to the vector field m comma n. This is not an accident. This is calculus. What if you want to find the flow lines to a vector field, right? Let's set aside the question of direction, right? Suppose you've got a vector field. So let's just set up the problem. If I can get you guys to see the answer without just telling it to you, it's better. So suppose you got a vector field that looks like this, right? We want to find curves in the plane which sort of follow this, right? Like, if I could do it like this, So these are integral curves or flow lines to f, let's say p comma q, right? So I'm graphing f. So my question to you is, what differential equation do I need to solve in order to find those flow lines? What differential equation takes the flow lines as their solution set? For what? Which? Grammar. Oh well. how about this? What, whatever. Anyway, what ODE takes the flow lines above as solutions? So that's my question to you. It should be in terms of P and Q. I'm looking for differential equation in Pfaffian form. Something dx plus something dy equal to 0. What do you guys think? It's not p dx plus q dy. That gives you the perpendicular lines to the flow lines. I heard a q dx minus p dy equals to 0. Some of you are like, no, it's p dy minus q dx, right? No, these are the same thing, but let's just keep one of them. Why is he right? What does the vector field q comma p look like? Q comma, so this, what is the vector, let's call it g, q comma minus p. What's that look like with relation to qp, pq rather? So if f is pq, right, where would q comma minus, what would q minus p look like? Here I'm where both p and q are positive, so you guys tell me, so it goes to the right, but it goes down, right? So your choice of sign makes this is like my g, right? Q minus p. The other equation, which I wrote and erased, would be the counterclockwise rotation of the vector field by 90 degrees, right? Like that would give me the other one up here. That would be what? That would be minus q p, right? Goes up. The other two choices, either of those directions is perpendicular to the other one, right? So if I find solutions of this, what do we say? Solutions are what? Perpendicular to q comma minus p, hence parallel to pq. Right? If it's perpendicular to either the red or the black arrow in my example 2, that means it's parallel with the flow, with the vector field which we're trying to find the flow lines to. Let's try this on for size. What happens if we try it out on my example 1? So what should we solve? What should we solve to find the flow lines, which we hopefully agreed were lines from the origin? We should solve minus y dx plus x dy, right? To find flow lines to x comma y. This is what I'm trying to convince you of. Of course, we can do that with separation of variables, right? This gives me what? Y dx equals to x dy. Separate, we got dx over x equals to dy over y. Integrate. Natural log absolute value of x equals to the natural log the absolute value of y. Add a constant to the left-hand side for my convenience. So that gives me, solve for y, we get y is equal to k times x through the usual algebra. Those are, of course, lines to the origin, right? Which, as I was arguing with you a few minutes ago, those are the flow lines to the radial vector field, right? It works, yay! Okay, so this is a question I started asking last year. Here's a vector field. Find the flow lines to the vector field. Is this a complicated question? It is not, right? You don't even really have to understand this whole discussion, right? What do you have to remember? You take the vector field you're given, right? You put the y with a minus, whatever's in the y part with a dx, put a minus. Put whatever's on the x part with the y and keep a plus. Solve it. That gives you the flow lines, right? Do you want me to take all the thinking out of it? Fine. All right. Why do we care about flow lines? Aerodynamics? Right, sure. Yeah, if we're looking, if our vector field's like a velocity field, then the flow lines really are sort of the, like the curves along which gas particles track or whatever, right? It does have that literal meaning. You can talk about an electric field, right? The flow lines to the electric field are the lines of force, you know, and so forth. You can look at flow lines for magnetic fields too. So flow lines are important, especially to the study of physics and vector fields. There is something we're assuming in all of this, which is that our vector fields are static, right? There's no time dependence to the vector field. But if you really study the heart of what we're doing, it probably wouldn't be much more trouble to try to solve problems with dynamic vector fields. What would you have to do there, though? What if you had a time-varying vector field? How would you handle that? Just a thought. How about a dynamic vector field? Something like f, which has a time dependence, right? So f would be something like, I mean, really it's got three variables. It's got x, y, and, technically speaking, I should really say f of t, x, and y, right? So it would be something like p, which is a function of x, y, and t in general, and q, function of x, y, and t in general, right? If you wanted to find a flow line, you know, like if you wanted to find curves which were flow lines to this at each time, I'm not sure that's possible. But if you wanted to try it, what do? Just try to solve this equal to dx dt, dy dt. And the question is, can you solve it, right? So you'd be trying to solve dx dt equals to p of x comma y comma t, and you'd be trying to solve dy dt equals to q of x, y, t. That if you could solve this system of two differential equations, right, then you'd have found the flow lines to this dynamic vector field. Now, we usually don't have a time dependence here, so we deal with what are called autonomous problems, right? Okay, enough about that. Don't worry, I don't think I have any problems like that to give you. I'm just I think it's worth spending a minute to think about, right? Because a lot of real-world problems are not a static situation, right? So how do you, what are orthogonal trajectories? Don't be scared of the terminology. It's very simple. Orthogonal trajectories, what is that? What does that mean? Okay, so we're given a curve or family of curves. And what are we looking for? Find another family of curves which are perpendicular to the given curve or family of curves. So it could be like this. You're given this curve, all right? You're looking then for this other family, which, if I could draw worth anything, trying. These are supposed to be perpendicular. Yeah. So I don't know what exactly happens here. Don't ask me to complete the end of the story there. That's what the differential equations is for. I mean, I can solve it. I can't draw it, all right? But this red family of curves, which meets perpendicular to the given curve, right? These are These should be right angles. These are the orthogonal trajectories, right? And it could be that you're given not just one curve, you're given a whole family of curves, right? Like this could be given. You're not just given one, you're given many curves, right? So if you've been studying, if you've understood some of the geometry I've shared with you already today for the problem of studying flow lines of vectors, it's not hard to see what to do, right? I mean, I think we can pretty well see the following claim is going to be true. If the given family solves m dx plus n dy equals to 0, then the orthogonal trajectory should appear as solutions to what? Minus n dx plus m dy. I hear what I want to hear. I think that's why it's, m and n are a horrible choice. It's just customary, but it's really hard to hear the difference. So, yeah. Now, in calculus 2, how do I usually treat? In calculus 2, what I usually say is what? I usually say something like, you have dy dx of the given curve equals to stuff, right? So, solve what? Dy dx equals to minus 1 over stuff for the orthogonal trajectories, right? Because then the slope will be minus the reciprocal of the original slope. That's what setting up orthogonal trajectories looks like if you've got dy dx sitting around ready to go, right? But a lot of times we have a differential equation in Pfaffian form, so it's nice to know how to find orthogonal trajectories given the differential equation in like dx dy format, right? These are equivalent. Here, I'll show you. This would be what? This would be stuff dx, right? Minus dy equals to 0. What's this if you put it in Pfaffian form? It's, what is it? It's stuff dy, right? Plus dx equals to 0, aka minus dx. I can't do math. Well, anyway, let me stop. You can see that. I think you can see. Well, this one, I guess I should multiply this by minus to make the usual the correspondence I just gave up here to match up, right? So like, this would be m, right? N would be minus 1. So there's minus m plus, minus n. Oh, have I done it wrong? Oh, I know. You know what's messing with me? This is really dumb. It's really, really dumb. But I should write this to see it in my current mental state. I have to write this. I'm an idiot. Of course, these terms commute. So now it looks like minus n. But it should be. Hey, I must have another error here. What? Hey. Huh. try this again. So this should go to dy, because that's minus n. I'm sorry. Should go to dx, because that's minus n dx, plus stuff dy according to that. And that is what I have there. So why am I... I'm sorry, guys. Let me stop this. Anyway. We can work an example. How about that? Don't be confused. There's nothing to be confused about here. There's a lot of different ways these orthogonal trajectory problems come to you, right? They're sometimes given in different ways, right? Sometimes you're given a differential equation. You're told to find the orthogonal trajectories. Other times you're given like a specific curve, find the orthogonal trajectories. Other times you're given a family of curves. So here's an example of that. It could be something like kxy equals to 1. Find the orthogonal trajectories to this. So what I do with a problem like this is I just differentiate it. So this would give me k times y dx plus x dy, right, equals to 0. So either k is equal to 0, right? If k is equal to 0, is there anything to think about there? No. So k is non-zero for interesting curves. So apparently the given family solves y dx plus x dy equals to 0, right? So to find the orthogonal trajectories, I go what? I go minus, let's see, flippity-floppity, right? So minus x dx plus y dy equal to 0. And then you solve. How do you want to solve that? Is it exact? I think it is exact, right? The partial derivative of the x component is 0 with respect to y. The partial derivative of the y coefficient is 0 with respect to x. So it's exact. We could solve it by the method of exact equations. This is the differential of what level function? D of what? So integrate the x coefficient with respect to x. What do you get? You get minus x squared over 2, right? What happens when you integrate the y component with respect to y? Y squared over 2. Now, whenever you do this kind of back of the envelope kind of calculation, you should think about it. Like if you actually take this total differential, does it get you back to here? I think for this problem, it's fairly clear that that does, right? The problem you just had on the quiz, you probably need to write some stuff down for, right? Oh, so there you have it. Minus x squared over 2 plus y squared over 2 equals to a constant. These are the orthogonal trajectories to the family of curves kxy equals to 1. Of course, this you could rewrite as y is equal to 1 over kx. These guys, by the way, are these things. They're actually hyperbolas that are rotated 45 degrees. So they have asymptotes of the x and y axes. Of course, these are hyperbolas which open vertically or horizontally, right? So these ones, their orthogonal trajectories look like this. And there's also these guys. My picture is not that great. There's asymptotes here for the orthogonal trajectories. The asymptotes for the black ones, the given curve, that's supposed to be a line, sorry. Not exactly quite a line, but so the dotted blue lines are asymptotes for the orthogonal trajectories, which are clearly hyperbolas which open up or down or left or right. The given family of curves is also hyperbolas that have the coordinate axes as their asymptotes. So, but there you go. I didn't have to draw this lovely picture to figure this out. I just let calculus be my guide, right? It gave me all of the orthogonal trajectories to that family of curves at the cost of a little integration. Any questions? So if I ask you, I say, here's a family of curves, find the orthogonal trajectories, I think you guys can do that, right? I mean, you're like, yeah, as long as there's not some horrible integration at the end of it, right? Like, not going to ask me integral of secant squared again, are you? I won't call you out. But you know the integral of secant squared is tangent, right? Or now you're remembering it. I don't know. It's kind of a bellwether for how much calculus you guys remember. What happens on that question? I'll tell you what, if you try to derive the integral of secant squared, that's tough. Right? That's an educated guess, and if you don't treat it as such, well, I think you could make it a lot of trouble. So guys, I want to spend the rest of the time here sharing with you some applications. One of the things we should talk more about is this, just geometric analysis. Suppose we had dy dx equal to e to the x. What could you say about the solutions to this differential equation? Could you tell me anything? Are the solutions increasing? Are the solutions decreasing? Are they concave up? Are they concave down? What can you tell me? How about this? I have dy dx equals to y squared. Or if I have dy dx equal to x times x minus 1, where are these solutions increasing? Where are they decreasing? If you find a solution. I'm not saying you find a solution. I'm saying you can answer my question without actually finding solutions. Why? Right, but there's an underlying idea you're using, which is what? What are solutions to differential equations? They're a function or an equation that when you plug it in, it satisfies the differential equation, right? What does the differential equation do? These differential equations tell you the rate of change of y with respect to x as it relates to either e to the x or y squared or x times x minus 1, right? So I can tell you just by looking at this, the solutions to this differential equation will be everywhere increasing because I know that e to the x is positive. And you know what? They'll also be everywhere concave up because the second derivative of this, what happens when I calculate, differentiate again? I get y prime prime equal to e to the x, right? So concave up everywhere too. This one, it's going to be increasing everywhere, yeah, but of course, y equals to 0. There's also the constant solution, y equals to 0, right? There's no constant solution to this. How about concavity? To find concavity here, I could differentiate again, right? So like y prime prime would be what? It would be 2y dy dx. But remember, we're talking about solutions to the differential equation. So what's dy dx equal to? It's equal to y squared. So I can tell you then that the solutions to this differential equation are concave up for where y is positive, and they're concave down for where y is negative. And I can do all of that without even so much as thinking about a solution technique. I do direct geometric analysis with the differential equation in calculus 1. We can do that. This one, where is it increasing? Where is it decreasing, the solutions? Eventually, I'll find my notes. Come on. I know I have notes in here somewhere. I hid them from myself on my own computer. How did this happen? Oh, there it is. Do you guys know how to analyze that? How about make a sign chart, right? Here's 0. Here's 1. I'm thinking of dy dx equal to x times x minus 1. Of course, this is a parabola. If we think about its values map out a parabola, right? As x-intercepts of 0 and 1, which means it looks like this. It's positive. It's negative. It's positive again. So solutions to this differential equation will be increasing to the left of 0. They'll be increasing to the right of 1. And between 0 and 1, they'll be decreasing. I can figure out concavity, if you want to. Differentiate this. What's y prime prime? Oh. Well, this is what? This is actually x squared minus x, right? So that's easier to differentiate. So 2x minus 1, right? So if we make a sign chart of y prime prime, that's got a 0 where? Half, right? So I can tell you, negatives, positives, my solutions to this differential equation will be concave up to the right of a half, and they'll be concave down to the left of a half. And I have not even so much as thought about how to solve any of these, right? And I've answered all those questions directly. That's an important idea that I think sometimes gets lost in the shuffle. And I may or may not actually test on it or even sign a problem on it, but it's something you should be aware of. Okay? Come on. Where'd you go? Somewhere in here I've got. So I have a stupid number of applied problems in the notes, right? You may have noticed. And some of them are from physics. A few of them are from electrical. There's a token population growth problem or two in there. So let's just kind of take a look at those. What time we have left here. I guess I could start with the last example and go to the first. That'd be more fun. I'll behave. All right, let me see if I have my laser. Oh, that's okay. I got it. Oh, thanks. It's okay. I just realized I need something else. All that partying I did yesterday, I'm still recovering. Let's see here. Oh, well, thank you. Now we can all relax. This example we did already. All right? First day, I think I did this example. We'll talk about the second one. Suppose that the population grows at a rate which is directly proportional to the population. Maybe you worked this in calculus too when you talked about differential equations, right? If the rate of population growth is directly proportional to the population that's there, we get what's called exponential growth, right? So this model is good for like bacteria in a petri dish or something, small isolated populations which don't have problems with what's called carrying capacity, right? Their growth is unbounded. So you do the math, dt equal kp, well that gives you dp over p is k dt, integrate, and there you go. P of t is p naught e to the kt. This is exponential population growth, right? Now, this same math happens for radioactive decay. So, like, if you got a stack of radioactive bologna or something, maybe there's not such a thing. Bolognium. There we go. Maybe it's got a half-life of 3 months, right? So the number of pieces of bolognium that are going to decay, it's statistical, right? You can't be sure that it's all going to be decayed in 3 months. If it's a half-life, what that means is statistically, a half of your bologna will have decayed to whatever it decays to after 3 months, right? Statistically. I mean, there's some outside chance that none of it will have decayed, and you'll still have that net amount of bolognium after 3 months, right? But the mathematics of that is that dn dt is equal to kn, where k is the decay rate. N is the total number of radioactive particles, right? So the continuum, I mean, think of n being a lot of particles, it's the same math, right? So exponential, but that would be decay, right? The difference here is we usually think about k being positive, the growth rate, right? Radioactive decay is negative, right? So, but same math. This is electrical engineering. We'll go on. Don't want to source, or you guys didn't react well to my first example, so I'm just going to move along here. Now here is basically this example is based on the discussion we were having before I got out the projector. I want to find a family of curves which are increasing whenever y is below 2 or above 2, and it's decreasing between minus 2 and 2, right? So what that means is I'm looking for essentially like this kind of function, but with y, right? So think about it for a little bit. Y plus 2 times y minus 2 causes y to be positive or negative in the appropriate regions, right? It causes y to be negative between 2 and minus 2 and be positive outside those regions, which is what I want for my solutions. Now, there's not a unique solution to this question, but this is just one solution. If I want to create a family of curves with a particular geometric profile, I can use this strategy. And then this is a problem we actually haven't done, but you could do because it's just partial fractions, right? Just partial fractions. We all know it. Don't worry, we'll get back to partial. Lest you think that I will leave you ignorant of partial fractions, have no fear. There's this topic called Laplace transforms. We do partial fractions out the wazoo when we get to there. So don't worry, it's coming. It's coming back. Anyway, integrate. Algebra, 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 algebra. Explicit solution, there it is. So, and since I like you guys, I even made a plot of it. As you can see, the solutions, in fact, do have what I wanted, which is increasing below and above plus or minus 2, and decreasing between those, just like I planned. So, all right. Anyway, here is a question about orthogonal trajectories. I think we've already talked about that enough today. Find the orthogonal trajectories. Hey, I think we actually, what do you know? We already did this example today. Okay, so, and this, oh look, this is the opposite version of this question. I started with this hyperbola, find the orthogonal trajectories. Well, I started with the orthogonal trajectories to this in this example over here, and we find that this was one of the one of the orthogonal trajectories. My point is, you could take any orthogonal trajectories problem, right, and start with the answer, and say find the orthogonal trajectories to the answer. It'll be the family you're given at the start. You know, there's this duality. The orthogonal trajectories to the orthogonal trajectories are the trajectories again. So yeah. So here's a better picture of what I drew on the board over there. Yay. Let me go on. This is not helpful. This is more important. I often ask this question on a test or something like it. It's a very common test question in here. Suppose the force of friction on a speeding car is given to be minus bv squared. All right? If the car has mass m and initial speed v naught and position x naught, then find the velocity and position as a function of time as the car glides to a stop. Assume that the net force is just the friction force, since the normal force and gravity cancel. In other words, I'm saying the motion's one-dimensional. All right. So Newton's second law gives me that m dv dt is minus bv squared. And then I solve it. It's a differential equation. Right? So first I solve for v. Separate, integrate, solve for v. Now I have to plug in my constant. I have to rewrite in terms of the given initial condition, right? So I plug in times 0. That gives me that c1 is minus 1 over v naught. So in fact, my constant is minus 1 over v naught. And then I just do a little algebra to solve for v of t cleanly. So there's my velocity as a function of time. It's the initial speed, initial velocity, divided by 1 plus bt v naught over m. What happens as t goes to infinity? It's always good to do some kind of check like this on our calculations for a physical problem. Yeah, v goes to 0. We should hope that, right? It's a friction force, right? It should slow the car to 0. If our intuition is worth anything, I think it is. Yeah. I'm more sure about yours than mine. And then to find the position, well, this is dx dt, right? So integrate again. And there it is. This is the integral of that is this. That's just calculus 2. You can do it. And then I plug in x of 0 being x naught. That tells me that c1 is x naught. And there you go. So as time goes to infinity, there's a maximum position it limits to. It doesn't actually get to, let's see here. What? Hey, I don't believe that. That seems wrong. Huh. I feel like the final position shouldn't be x naught. Interesting. Intuitive, I feel like there must be a problem with this, and I don't know where it is. So I'll leave that to you guys to tell me about. If we can find it next time, we'll start class with that, okay? Or tell me I'm right and that my intuition's wrong, right? See, the trouble I'm having is time goes to infinity. Oh, I'm an idiot. What happens as time goes to infinity? Problem solved. This does not go to 0. This goes to log of infinity, which is infinity, right? So this is just a little bit disturbing, right? The velocity is going to 0, but the position is going to infinity, right? It's just going to infinity very slowly. This is not a problem. This is just calculus. Let's see here. Newton's law of cooling is also a very popular application. It says that the rate of change of temperature of an object is proportional to the difference between the temperature of the object and room temperature. Technically speaking, this is not a differential equation. It's actually a family of differential equations. See, because you got two choices. You got the proportionality constant K, and you also got the room temperature T, right? So to find a specific solution to this, you actually need 3 pieces of data. You need one piece to fix the K, you need another piece to fix the room temperature, and you need yet another piece to fix the actual initial data for the problem, once you specify a K and an R. Now usually these problems come stated with a room temperature, and then 2 other pieces of data, right? That's typically what happens with the Newton's law of cooling. Like this one here, but it's actually just integrating factor method. You can also do separation of variables to solve it. It's all good. Long story short, you get T of t is the room temperature plus some constant times e to the minus kt. So as what happens as time goes to infinity, this piece does what? Drops to 0, and so everything goes to room temperature eventually, right? This is kind of morbid, but let's see here. So this one I'm given that my initial temperature of the coffee is 150 degrees, and then after 1 minute it cools to 120 degrees. I'm also given that the room temperature is 70 degrees. Like I said, 3 pieces of data. Yep.
What if the room temperature increase though? Because
Oh, we assume that the room is large enough that the coffee can't increase the temperature of the room. Yeah, that's an assumption. But yes. Otherwise, that would be another kind of problem. Then we'd have to also have equations for the room. Yeah. Here's a question. How do you model ice melting in a glass? See, because there you have ice and you have water, and you have the interface between the ice and the water. It's time varying, right? These are actually current research problems in differential equations. They're called free boundary value problems. See, because the boundary for those that you're trying to solve, it's moving. It's not static. This is the classic free boundary value problem, I think it's called. Related to that would be sort of the equations which govern like micro-sized drones flying. Also a problem of free boundary value problems. I heard a talk from a lady at NC State who studies these. She said that they wouldn't have applications for the government. So, like micro-sized drones, no. Something the government wouldn't be interested in. But anyway, so you solve it and you get this, and there it is. So, all right guys, well, next time I may talk about more applications, or I might just go on. You guys can ask me questions, of course, next time if you got them.